Our objective is that students will use the catapult to explore parabolic motion, kinematic equations, and analytic geometry in order to successfully analyze data recovered from the trials, allowing them to get conclusions about the importance of the understanding of these topics. First of all, we need to explain certain things before we start. In physics, there are several different kinds of motions. They go from linear motion to rotatory motion, reciprocating motion, irregular motion, uniform motion, and parabolic motion, among many others. In this work, we are only going to focus on one specific kind of motion, parabolic motion. This motion includes what is known as a projectile. A projectile is an object upon which the only force acting on it is gravity. Gravity, which is a downward force directed towards the center of the Earth, causes the projectile to accelerate in that direction. However, the force of gravity does not interact with the horizontal velocity that the object has, since the perpendicular components of the motion are independent of each other. This means that while the motion in y-axis is affected by gravity, the one in x-axis is not. This means that one is a constant acceleration motion and the other is a uniform rectilinear motion. Calculating this kind of problems is easy when you have at least some active knowledge in physics and mathematics. The solution for the equations that we know as kinematic equations need a lot of algebraic understanding. Each of the kinematic equations includes 4 variables. If the values of 3 of the 4 variables are known, then the value of the 4th variable can be calculated. In this manner, the kinematic equations provide useful means to predict information regarding an object's motion if enough data is known. The variables that are involved in these equations are displacement, velocity, acceleration, and time. For instance, the variable d stands for displacement, t stands for time, a stands for acceleration, and v stands for velocity. This last one has a subscript with the letter I or f, depending if the velocity corresponds to initial or final velocity. Each of these 4 equations accurately describes the mathematical relationship between the parameters of an object's motion. Our project is also based on Hooke's law, which states that for relatively small deformations of an object, the displacement of size of the deformation is directly proportional to the deforming force or load. Mathematically, Hooke's law states that the applied force F equals a constant k times the displacement or change in length, x, or F equals kx.
Now we're gonna proceed with the mode of operation. First, an object is located at the bucket of the catapult. It is worth to say that the mass of this object is known in order to proceed with further calculation. The mass of this object is 20 grams, which is equal to 0.02 kilograms, in order to proceed with international units. Then, an external force pulls the arm block of the catapult in a specific angle, which elongates the spring that is attached to the crossbar of the machine. Finally, the external force at the specific angle is disengaged and the catapult arms block returns to its original state, releasing the object located at the bucket. Today we're going to show you how our experiment works for our physics and mathematics project. Firstly, what do we have here? Here, as you can see, we have a catapult. Which are the main parts of the catapult? As you can see, it has a bucket, which is right here. It has an arm block, in which the bucket is sustained and it is adjusted to this crossbar of the catapult. Also, we have 2 arm blocks by the side of this arm block. And also we have a crossbar right here, which is the one that attaches the spring to the upper part of the center arm block. So and right here we have a base in order to attach all the arm blocks and be able to work. Now, what does this catapult does? As you know, all catapults launch items. So here, when we make the spring stretch, and we put an item on here, it will launch something. Now we're going to proceed with what do we have. Here we have 500 milliliters of water, which can be converted into 500 grams. So this is the way that we're going to use in order to pull the catapult and let it launch something. How we're going to sustain the 500 grams with this tape. This tape is so resistant that we're going to cut it when we want the catapult to be launched in order to release this weight. And what are we launching? We're launching this wine cord, which has a mass of 5 grams, and we're going to proceed with the experimentation process. We're going to proceed with the launching time of the catapult. So as you know, first we need to locate this cord, this wine cord, in order to let the catapult launch something. So we're gonna put it inside the bucket. Well, now we have the bucket right there, and as you can see here, we have our weight that is hanging from the catapult center arm block, which makes the string to elongate. And now we're gonna launch our item. We're gonna cut the tape that helped us sustaining this weight. So now we're gonna see what happens. And as you can see, the wine cord was launched. We cannot determine the parabola form between the bucket and the final position of the item experimentally, but we can do that theoretically. That's what we're gonna prove by analyzing the final or initial velocity of at which the wine cord was launched. This will help us applying kinematic equations in order to determine the highest point at which the wine cord, as you can see, is right there, was launched. And we're gonna determine different parts of the parabola, which will be the vertex, the focus, and the lactus rectum, and different points of the parabola. So you can see how theoretically you can determine an experiment without doing it experimentally. Thank you. And thanks to my assistants right here, Luis. Thank you guys for your attention and watching our video.
Following the previous methodology, further calculations can be done. First, the value of the constant K can be determined by attaching the spring from any horizontal surface and hanging a weight from it. After locating the weight W, just measure how much the spring is stretched with respect to its original length and name this stretch changing next. Now you need to isolate K from the first equation, which is F equals K times X, and simply divide the weight of the mass attached by the change of K, and the result will be the constant K of that specific spring. K equals W, which is weight over the change on X, which is the change of a stretching. We take as a base an output of 300 grams, which equals 0.3 kilograms, and substitute the values into the equation, considering that W weight equals mass times acceleration, m times a, and that the spring at the original length had a value of 7.7 centimeters, and after hanging up the weight from it, it changed into 12.2 centimeters. The difference was of 4.5 centimeters equals to 0.045 meters. Then we substitute the values into the equation considering international units. K equals W, which is weight times change in X, equals 0.3 kilograms times 9.8 meters per second square, which is the value of gravity, divided by 0.045 meters, which is the difference when hanging the weight. This equals to 65.33 kilograms per second square. This is the value of K, which will never change. Now, having the value of K, we need to look for the value of X, which is the distance that the spring moved from its equilibrium point to that specific launching angle, when the 500 grams, which is equal to 0.5 kilograms, were hanged. The original length of the spring is 7.7 centimeters, and the length when the 0.5 kilograms were hanged was 60.5 centimeters. If we subtract these quantities, we obtain 8.8 centimeters, which is equal to 0.088 meters. Then, having the value of the elongation of the spring, which is x, the sum of the mass of the external force and the mass of the released object, m, and the constant of the spring, which is k, we can obtain the velocity at which the object will be released. You can see the substitution of the obtained quantities into Roberts-Hooke's equation at the bottom of our slide. Then, after obtaining the final velocity, also known as the initial velocity at which the object will be launched, and knowing that 40 degrees is the standard angle at which the object will be released because of the weight that is applied into it, we can calculate the highest point that the item will reach with kinematic equations. Description of the device. Our device, as said before, is a catapult. This device follows the traditional basic form of a catapult. We construct the machine with wood and attach the pieces with wood nails, so it will be easier to handle. At first it was difficult, but at the end we were able to know what good teamwork can achieve.
What are the benefits of our project? Its students will have a better understanding of parabolic motion and quadratic equations. We will get junior high students interested in science, and we will create a more interactive class that will improve students' school life. Also, we will give young minds opportunity to expand their knowledge in the science field. And the most important of all, we will encourage students to use the knowledge that was learned with our project.
Our conclusion is that as a team, based on the methodology we follow and the results we obtain, we can say that our device will help students understand the application of the theory behind parabolic motion and first plane, and how the study of parabola forms the point of view of analytic geometry will help them to justify their knowledge. This also will be attractive to them since they will be able to predict where the projectiles will fall, and they will love it.
We also hope that students will use the information they are given in their physics class to understand the importance of empirical knowledge, to fully comprehend anything regarding the physics or mathematics of our world.